Hello everyone. So today we will be discussing the metamorphic reactions. So metamorphic changes generally involve recrystallization of pre-existing phases. Recrystallization means the phases which are existing in the rock. They are in the rock before the metamorphism is taking place, and that these phases they recrystallize once more. So this is known as recrystallization of pre-existing phases and metamorphic mineral formation by reactions. And metamorphic mineral formation means by through reactions many new metamorphic mineral or any changes in the metamorphic mineral or any modification of the earlier mineral, so these all take place through reactions. So this is also a kind of metamorphism. The reactions are also a kind of metamorphism, and the recrystallization is also a metamorphism. So there are generally 8 type of metamorphic reactions: phase transformation, exsolution, solid-solid net transfer reaction, devolatilization reaction, continuous reactions, ion exchange, redox, and reactions involving dissolved species. So we will be discussing all one by one. So phase transformation. In phase transformation, these are generally isochemical and they are dependent only on temperature and pressure. So phase transformation this is also called polymorphic transformation. Here we have an example of calcite and aragonite. So calcite, we know that calcite has a formula CaCO3 and aragonite also has a formula CaCO3, but calcite and aragonite they exist in different pressure temperature condition. See, if we see the pressure, this is pressure, this is temperature. If we see this pressure temperature diagram, we can see that calcite is a low pressure and a low pressure high temperature mineral. Since it is existing in this zone, these are all low pressure high temperature, and aragonite has a lower temperature but a higher pressure. So aragonite is a high temperature high pressure mineral, while calcite is a high temperature mineral. Dividing these two is the line. This line this is the pressure temperature equilibrium curve. Below this curve calcite is stable and above this curve aragonite is stable. So if we have calcite and we increase the pressure, so the calcite will be transforming into aragonite. This is a polymorphic transformation. We don't see any chemical changes. The chemical formula is still the same. We had COCO3 and we are still having COCO3, but this COCO3 has a different structure. These are the different arrangement of atoms. That's why it is known as aragonite. We have another example of aluminosilicates. We know that Al2SiO5. It is andalusite, sillimanite, and kyanite. Sillimanite, andalusite, and kyanite, all three have the same formula, but they are polymorphs of each other. They are stable in different pressure temperature condition. We can see from this pressure temperature diagram, andalusite is a generally a low pressure, low temperature mineral, while sillimanite is a high temperature mineral. Kyanite is a high pressure mineral. So these lines, this line, this is a PT equilibrium curve for kyanite and sillimanite. Similarly, this line, this is for andalusite and kyanite, and similarly this line, it is for andalusite and sillimanite. in this line, this green line, along this line both andalusite and sillimanite are stable, but along this blue line andalusite and kyanite are stable. Similarly, along this red line kyanite and sillimanite are stable. So along this line both kyanite and sillimanite coexist together. Along this blue line kyanite and andalusite are coexisting together, and along this green line this sillimanite and andalusite are coexisting together. And at this point, this center point here, all the three phases coexist together. So now we'll be moving to X solution. We had already seen this diagram in case of igneous petrology. We already know that at higher temperature we have a continuous reaction between orthoclase and alvite, and feldspars are formed and they occur as a single feldspar. But if I change the temperature, if now, since see this was 1020 degrees centigrade, this may be around 900 degrees centigrade. If I now reduce the temperature, this solid which was initially here with decrease in temperature will reach this point G. At G it will dissolve into two different feldspar. One will be overrich and the other will be heavy rich. So this is also a kind of metamorphic transformation or a metamorphic reaction. A single feldspar is getting transformed into two separate feldspar. We also see two type of textures here. One is perthite and another is anti-perthite. Solid-solid net transfer reactions. Solid-solid, since the reaction name is such, solid-solid means it involves only solid. So the first point is it involves only solids, and it is also different from the polymorphic transformation as it involves solids of differing composition. In polymorphic transformation we were having either aluminosilicate, that was Al2SiO5, or a calcite or a aragonite CaCO3. We were not having any compositions of different which differed from each other. They were all of same composition. If it was CaCO3, it was only CaCO3, because both calcite and aragonite, they have the same composition. Similarly, andalusite, kyanite, sillimanite all have the same composition. But in case of a solid-solid net transfer reaction, we have solids that differ in composition. They have different compositions. This is an example of solid-solid net transfer reaction. We can see that this is jadeite and quartz. If we see, this is very similar. If I now see the pressure temperature condition here, we know that this is a high pressure low temperature condition. So this is, we can generally say that this is a blue cyst phases condition. Blue cyst phases is a high pressure metamorphic phases. And if we see now this one alvite, it has a generally higher temperature and a lower pressure. So if now the temperature increases and the pressure reduces, or any case, if suppose I have a composition here at this point, now if the pressure is reducing it will enter into this albite zone. This line, this line, this is the dividing line. This line, sorry, this line is the pressure temperature equilibrium line for jadeite plus quartz and albite. So above this line, jadeite and quartz are stable, and below this line, this side we have jadeite plus quartz, and below this line we have albite. So if the pressure temperature condition changes and it is such that we need to jump this line or we need to come below this line, in that case jadeite and quartz will be now not stable and they will be converting into albite. This is the reaction. NaL Si2O6, it is jadeite, SiO2 is quartz, they give albite. This reaction is the solid-solid net transfer reaction, because both these solid are reacting with each other and they are getting converted into a new solid. This is the new solid, and jadeite and quartz, they react with each other. So if the minerals contain volatiles, so we know that volatiles can be H2O, CO2, etc. These are all volatiles. So if some mineral contain volatiles in them, then that volatile also must be conserved in the reaction so that no fluid phase is generated. Because our reaction, the name of this reaction is solid-solid net transfer reaction. So if the reaction is such that it liberates a new fluid or a new phase, a new liquid phase, then in that case the reaction will be not solid-solid net transfer, because a new fluid phase is getting found. So for that, if a mineral is having a volatile in it, it is containing volatile, then that volatile also must be conserved and no new fluid phase must be found. This is an example of how this conservation is taking place. Mg3Si4O10OH2, this is talc. It reacts with astatite to form anthophyllite. We can see that this OH whole 2, this is the hydrous phase of talc. This OH whole 2 phase is getting conserved in this anthophyllite structure, and it is not liberating any H2O. If for example by chance we had the reaction would be such that a H2O field is getting generated, it is getting generated, in that case this reaction will be now not be considered as solid-solid net transfer reaction. Since we don't have any independent H2O phase, we don't call this, we call this as a solid-solid net transfer reaction. Now devolatilization reaction. So devolatilization means volatilization means the volatiles that are present in the structures of any mineral. Devolatilization means that volatile phase is getting removed from that mineral structure and it is forming an independent phase. H2O, CO2 systems are generally most common, and H2O and CO2 both are volatiles. So this devolatilization reaction depends on pressure, temperature, and the most important, the partial pressure of the volatile species. Since we have volatile species, the volatile species, they have a pressure. They they impart a partial pressure. This partial pressure is also very important for the reaction because it plays a great role in determining whether the reaction will be moving towards right or towards left. We will be seeing that in next slide. The first one is dehydration. Dehydration means removal of H2O. H2O is water. So if the water is getting removed from the structure of a mineral and it is getting formed, it is water is generated as an independent phase. In that case, the reaction is termed as dehydration reaction. We have an example: muscovite plus quartz gives K feldspar plus sillimanite plus water. So since water is getting formed here as a independent phase, this reaction is called dehydration reaction. This reaction depends on the partial pressure of H2O. Why H2O? Because here the volatile phase that is getting generated, that is forming here, is water. Since water is the volatile phase here, the reaction depends on the partial pressure of that water. The reaction here is KAl2Si3O10OH2. This is muscovite. This is quartz. Muscovite has a hydrous phase. That means muscovite has water in its structure. So it reacts with quartz to form K feldspar, that is orthoclase, plus sillimanite, that is Al2SiO5 plus water. This is a dehydration reaction because water is getting removed. Muscovite is losing its water and water is getting formed as an independent phase here. So this is a dehydration reaction. In this case, this is the pressure side, this is the temperature. This line, this is the equilibrium line. This is the pressure temperature equilibrium line. This side muscovite plus quartz is stable, and this side K feldspar plus sillimanite and water is stable here. If my pressure temperature condition is such, now suppose I have a temperature of now 600 degrees centigrade, in that case muscovite plus quartz will be getting converted to K feldspar plus sillimanite plus water. If now the temperature is getting reduced, now the temperature is 200 degrees centigrade, then in that case this will be getting converted to back this side. So it depends on the temperature and pressure. This equilibrium line has a partial pressure of H2O equal to the lithostatic pressure. This is called the equilibrium line. At equilibrium, partial pressure of water is equal to the lithostatic pressure. Suppose now let us take a condition. Suppose there is a condition where water is withdrawn from the system. Water is withdrawn from the system means the water from the system is getting removed at some point on this water saturated equilibrium curve. This line where Ph2O is equal to P lithostatic pressure, the partial pressure of water is equal to the lithostatic pressure. This is called the water saturated equilibrium curve. So in such a case that water is removed from the system, if I remove the water, it is obvious that the partial pressure of the water will be also getting reduced, but the lithostatic pressure is still the same. Since my system is the removing, since the system removes water, or the water is removed from the system, the partial pressure of water will be now less than the lithostatic pressure. So in this case, a principle is applied here. This principle is known as Le-Chatelier's principle. Le-Chatelier's principle says that removing water at equilibrium will be compensated by the reaction running towards right, thereby producing more water. So now let us see with this help of this diagram. This line, this green line, I am highlighting it here. This has partial pressure of water equal to the lithostatic pressure. Now the water is removed from the system. If the water is getting removed from the system, the reaction will be running towards right. The reaction will be running towards right means the reaction will be running towards K feldspar plus sillimanite plus water. This was the reaction. The reaction, this side is the left side and this side is the right side. So if water is removed from the system, the reaction will run towards right. That means if the water is removed and the reaction is running towards right, then more and more water will be produced. And this is because since the water is removed from the system needs more water. The system needs more water in order to reach to the equilibrium. In order to reach to once more, this we had equilibrium here. Now the water is getting removed. If the water is getting removed, then the partial pressure of water is decreasing. Since the partial pressure of water is now less than the lithostatic pressure, the system will try to produce more water so that it can again reach that equilibrium state. Everything in this system wants to be in equilibrium. Until and unless we have equilibrium, we don't have equilibrium, there will be a reaction taking place. Either it will be moving towards right or moving towards left. Suppose I supply more water, then the reaction will be moving towards left. It will be producing more muscovite plus quartz so that it will reach equilibrium. Since we are having the partial pressure of water less than the lithostatic pressure, the reaction will be moving towards right, means the reaction will be moving towards K feldspar plus sillimanite plus water. Since the water as an independent stage is a product, so the shortage of water is now compensated by production of more water. And if now more water is getting produced, that means the field area of this will be increasing. See, initially at equilibrium, the K feldspar, this area, this is the area for K feldspar, sillimanite and water, and this was the, I am highlighting it with a different color, this was the area for muscovite plus quartz. See, this area is the area for muscovite plus quartz. Now I have removed water from the system, so the system will move towards left, thereby producing more water. If it will produce more water, then the amount of muscovite and quartz in the system will be getting consumed. Otherwise, how the system will produce more water? It will produce water by consuming this muscovite and quartz. If this muscovite and quartz are getting consumed, in that case the area, the muscovite plus quartz area will be getting decreased. So suppose it will come to this point now. So now the area for K feldspar plus sillimanite plus water is this bigger area, and the muscovite plus quartz area has decreased because the system has produced more water. So in order to produce more water, it consumes the muscovite plus quartz. Since the muscovite plus quartz is getting consumed, the area, the muscovite plus quartz area in this graph will be also getting decreased, and this K feldspar plus sillimanite plus water area will be increasing. So this we had now discussed that in water is, if water is removed from the system, then partial pressure of water will be less than the lithostatic pressure. But in how this water is getting removed? So water is getting removed from the system in two ways. First one is drying out of the rock. If the rock is drying, then the water is evaporating or it is getting consumed in any way, and the rock is getting dried. So if the rock is drying, the water is removed. In that case, the partial pressure of water will be less than the lithostatic pressure. And in other case, if water in the fluid becomes more diluted by addition of any other component. Suppose I have only water. In that case, I add now CO2. If CO2 is added to the system, then the water as a fluid gets diluted. Since the water is getting diluted, in that case the partial pressure of water will be reducing. So if the partial pressure of water is reduced, so the reaction will move towards right, thereby producing more water. This diagram, this is a temperature and composition diagram, and we are using a temperature and composition diagram here because this temperature of an isograde based on devolatilization reaction is sensitive to the partial pressure of the volatile species. As we had discussed here, this diagram we had a temperature and pressure. So this temperature isograde, the temperature is sensitive to the partial pressure of the volatile species. So we use an alternate diagram. This is a Tx diagram. Temperature and X H2O means the moles of H2O present. Suppose I have 3 moles of fluid. In this fluid I have 1 mole H2O and 2 moles CO2. So in this case X H2O will be 1 by 1 plus 2, this 1 by 3 or 0.33. In that case I will be plotting it in this is 0.3 at some this point, so it will be 0.33. So for XH2O the temperature now will be this one. So if for means the main concept here is the system is now dependent on the composition of H2O or the XH2O and the temperature, and we have a fixed pressure here. The pressure has been fixed here to 0.5 GPa. In this case we are having a variable pressure and a variable temperature, but now we are fixed the temperature and only the temperature varies and the composition varies. So for if this is XH2O equal to 0.33, if I have XH2O equal to 1 means I have only water, I have no CO2 or any other type of fluid that has diluted it. in that case the reaction or the change from muscovite plus quartz to K feldspar plus selenite will take place at a higher temperature. But if I have no water, I have only less water, suppose I have a this is 0.1, in that case I will be having a reaction temperature very low. And similarly the slope here is gentle at when x(h2) is equal to 1, and when x(h2) is 0 or x(h2) is less, that is slope is steeper. Then this is decarbonation reaction. In decarbonation reaction, CO2 is released, so calcite plus quartz they give wollastonite plus CO2, and this is the diagram for calcite plus quartz field. This is xCO2 now. See, similarly when xCO2 is 1, the reaction is at a higher temperature. The reaction or the conversion from calcite to takes place at a higher temperature, and when this is at a when xCO2 is very less, or the amount of CO2 in the system is very less, the reaction takes place at a lower temperature, and the slope here is gentle and the slope here is steeper.